So this video is an introduction to the sine and cosine ratios, and it follows along after the introduction to the tangent ratio that we just saw last night. So as a reminder, the tangent ratio in a right triangle is the ratio of the length of the side opposite an angle to the length of the side adjacent to the angle. So for angle 1 here, the side opposite the angle is angle A, and the leg adjacent to the angle is angle B. So the tangent of angle 1 is the ratio of A over B. Similarly, for angle 2, the side opposite angle 2 is B, and the leg the leg adjacent to angle 2 is A, so the tangent of angle 2 is the ratio B over A. And that's true for tangent. Tangent is one of the trigonometric ratios that we have, but there are two others that are often used that sort of fill out the main set of three trig ratios that we have. The first is called the sine ratio. And the sine ratio of an angle is the ratio of the length of the side opposite the angle to the length of the hypotenuse. Now, this is specifically in a right triangle, as you can see by the fact that we're referencing hypotenuses. So go ahead, pause the video, write down everything you see on this screen, come back when you're ready to look at it in more detail, and move on to the next one. So for a sine, what we have, if we're looking at angle 1, the side opposite angle 1 is A, and the hypotenuse is C, so the sine is the ratio of A to C. Similarly, for angle 2, the side opposite angle 2 is B, and the hypotenuse is C. So the sine of angle 2 is B over C. Really, that is all that it is. These ratios are just literally that, the ratio of one side of a right triangle to the other. There are lots of other applications when we get into Algebra 2 and pre-calculus, but as far as what we're looking at in geometry, we're focusing on them as the ratio of the lengths of sides of right triangles. The last ratio that we'll talk about as a part of this class is something called the cosine ratio, which is the ratio of the length of the side adjacent to the angle to the length of the hypotenuse. Go ahead, pause the video, write down everything you see on this screen, come back when you're ready to look at it in a bit more detail, and move on to some practice problems. So for angle 1 in cosine, the side adjacent to angle 1 is length B, and the hypotenuse is C. So the cosine of angle 1, abbreviated COS, is the ratio B over C. Similarly, for angle 2, the side adjacent to angle 2 has length A, and the hypotenuse has length C. So the cosine of angle 2 is literally just the ratio of A to C. Similar to sine in a lot of ways, but sine involves the opposite side to the length of the hypotenuse, and cosine involves the adjacent side to the length of the hypotenuse. So what we've seen as a result of all three of these trig ratios is that tangent is the ratio of opposite to adjacent, sine is the ratio of opposite to hypotenuse, and cosine is the ratio of adjacent to hypotenuse. And frequently we remember those by putting them in the order of sine, cosine, and tangent, and abbreviating what they are with the sides in the right triangle that they're referring to. So if we look at sine being opposite over hypotenuse, we abbreviate it SOH, sine opposite hypotenuse. For cosine, we would abbreviate it CAH, cosine, for adjacent over hypotenuse, and tangent is opposite over adjacent. And this leads to this phrase that lots of people remember from trigonometry or geometry when they learn it, which is Sohcahtoa. And Sohcahtoa allows us to remember the ratios that sine, cosine, and tangent refer to when we're talking specifically about right triangles. Again, they have lots of other applications and lots of other meanings outside the world specifically of right triangles. But when we're talking about right triangle trigonometry, which is what we're looking at right now as a part of the geometry class, this is how we can remember what sine, cosine, and tangent represent. Sine opposite hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent with Sohcahtoa. So if we had a right triangle that looked like this, where we had triangle ABC, and we had sides 5, 12, and 13. You'll recognize it from the tangent video. We could talk about the sines of each of the angles. So if we look at angle A, the side opposite angle A, remembering so, sine opposite over hypotenuse, the side opposite angle A is 5, and the tangent, or not the tangent, the hypotenuse is 13. So the sine of A is 5 over 13. Similarly, the sine of B, opposite, is 12, hypotenuse is 13. So the sine of b is 12 over 13, literally opposite over hypotenuse. Now if we take a look at cosine, remembering CAH for in Sohcahtoa, cosine being adjacent over hypotenuse, the angle adjacent to A is 12, and the hypotenuse is 13, so the cosine of A is 12 over 13, and the cosine of B is the adjacent side, which is 5, over the hypotenuse, which is 13. So if you know the lengths of right triangles, the lengths of sides of right triangles, you can easily set these up. Just as in the tangent ratio, we can also set them up as ratios. For example, if we didn't know what the side opposite A was, but we knew the size of A, and we knew the hypotenuse was 13, we could say sine of 32 degrees is equal to x over 13. Here you're going to find the values of x and y. Pause the video, come back when you're ready to see the answer. So in this problem, we know a 37-degree angle, and we know the hypotenuse is 35, which means we'll probably use sine and cosine. So sine of 37 is the opposite, which is x over 35. Here, we can sort of multiply by 35 on both sides to get that x is 35 times the sine of 37 degrees. We end up with something in the vicinity of 0.6018, and so 0.6018 times 35 gives you something in the vicinity of 21.063. Similarly, when we have angle y, except this time we're going to use the cosine of 37 degrees, which is now equal to y over 35. The cosine of that angle as 37 degrees is 0.7986. And we'll multiply both sides by 35 again. And multiplying 0.7986 times 35 gives you a value for y of about 27.951. All right, moving on to the next type of problem. Again, we're going to have a missing x and a missing y. Go ahead, pause the video, calculate these values, come back when you're ready to see the answers, and move on. So for this problem, it's very similar to the one that we had before. We have an x and a y on the legs and a hypotenuse that we know. So if we are looking at the 58-degree angle that we have, let's start with sine like we did last time. So we have the sine of 58 is equal to y over 120. We can multiply both sides by 120 as we did before to get that 120 times the sine of 58. And if we actually go through and take the sine of 58, we end up with 0.848 is equal to y, and multiplying that by 120, we get that y is equal to 101.76. Then for x, we have the cosine of 58 being equal to x over 120. Multiply both sides by 120. The cosine of 58 is 0.5299. And when we multiply that by 120, we end up with 63.588. All right, next problem that we have here is something similar to what you had seen in the tangent ratio, a bit of compound triangles. Here, two triangles that are set next to each other. We got some right angles there. We got an x and a y. Go ahead, pause the video, calculate the values of x and y, come back when you are ready to see the answers, and move on. So here we can use both triangles for this one. There's a few things we don't know, but also a lot that we can say. For example, both hypotenuses of these triangles are 30, which means that the overall triangle is isosceles, and this angle here is also 70 degrees. So that by the isosceles triangle theorem. So we have the sine of 70 equals x over 30, and we have the cosine of 70 is equal to y over 30. Now, the sine of 70 is 0.9397. Multiply that by 30, and we end up with 28.181, or 191 rather, for x. Cosine of 70 is 0.342. Multiply that by 30 and end up with 10.26. This time you notice a plane flying in the sky at about 30,000 feet high. If you measured the angle between where you see the plane on the ground and where the plane is, it would be 8 degrees. And we're asking how far the plane is from you, or how far you are from the plane, along that line of sight. So if you imagine you had a string connecting you in the plane, how long would the string be? So go ahead, pause the video, see what you can do here, and then come back when you are ready to see the answers and end the video. So here we have an example of a person standing on the ground, you, and a plane flying here somewhere. And what we know is that the plane is 30,000 feet high. We know that you're looking at the plane, and the angle that your sight makes with the ground is 8 degrees. This is called an angle of elevation. And so now we want to know how far from you is the plane. What is that value right there? We could also ask about the value along the ground to where the plane is, but in this particular one, we're going to ask for the hypotenuse there. Again, we have a sine situation where we know that the sine of 8 degrees is equal to 30,000 over x. We can flip around, multiply by x, divide by sine of 8 to get x is equal to 30,000 divided by the sine of 8 degrees. And so the sine of 8 degrees, when we actually go through and calculate it, is somewhere in the vicinity of 0.1392. And if we were to take 30,000 and divide it by 0.1392, we end up with x is equal to 215,517 feet, approximately, a long way away. Now, if you had tried to find the length along the ground, that's why, we could have said that the tangent of 8 is equal to 30,000 over y. The tangent of 8 is about 0.1405. And so if we actually do that calculation, we would find out that y, the distance on the ground, is about 213,523 feet. So that's a brief introduction to the sine and the cosine ratios. Again, this is specifically as it relates to right triangle trigonometry. As we study it in geometry, sine, cosine, and tangent have lots of applications and other meanings and uses out there, but specifically for what we are looking at, this is how we're going to use them.